This is it, guys. This is the last lesson of new material that I have to go over with you. And I know that's incredibly exciting until you preview the massive length of this stinking lesson. It's so long and tedious. So this is definitely going to be broken into a couple videos. There's nothing I could do about that, but it is the last one, so there's hope for that. As a reminder, this will not show up on the AP test, so those of you who are still going to take that, this will not be material that's covered. The nice thing about this is, though, we're talking inference for slope, so we're going to be talking about regression lines, something that we did first semester, so it's probably been a while since we've really looked at this. There were a couple review problems that we saw in February or March, but it's kind of nice to interact with this again. And we will still be talking about confidence intervals and hypothesis testing, so it is still keeping that fresh as well. So this is lesson 3 of unit 11, and we know scatter plots are supposed to be looking for a linear relationship. That's what we've used it for. So looking for something between a quantitative explanatory variable and some quantitative response variable y. So we're talking quantitative stuff now. So we're out of the qualitative charts, categorical stuff. We're going to be using these least squared regression lines. We could calculate it to make predictions. That's what we did back in the other chapter. If the data is from a random sample of a larger population, we can actually keep asking more questions, though. So we don't have to stop at what we did first semester. We can not only look for, is there really a linear relationship? Is it just random chance that we're seeing this relationship? And in the population, how much will the predicted value of y change for each one increase of x? And we can find a margin of error for this estimate as well. So because of this, we can, there's a whole setup of stuff that we can do in here. What I really want to get at, though, is to show you how we can estimate and test claims about the slope for the population regression line, the true regression line for some data. So we're collecting a sample, we're going to make inference for the population. We got to understand the sampling distribution of the sample slope. We've talked about sampling distribution of sample means, sampling distribution of sample proportions, different type of sampling distribution. Now, we would have done an activity where I made you get in groups. We selected a sample of 15 cards representing Old Faithful eruptions. You would calculate your least squared regression line, and you would get a slope. And then I would make your group report your sample's slope. And then we would do this again and again and again until we'd have about 20 of these slopes. And so I would make everybody put all their slopes up on the board. We'd be reporting them as B, because if you remember when we did this, it was y hat equals A plus BX. So this is our slope. So there would be all these B's on the board, and we would be looking for the shape, we would be looking at the center, we would be looking at any unusual features, the variability of it. This is made up B values, but this is what we would have done. So what we have below this, though, is not based off of a sample. Excuse me. This is a figure showing this exact same relationship, showing the relationship between the duration of eruptions of Old Faithful and the interval of time in minutes until the next eruption. And now this is for all 263 eruptions during a particular month. So since this is all of them, this is the true regression line, which is what's down here, sometimes called the population regression line. You usually don't have that for an entire population. That's why we rely on the sample regression line. So it would be when you took your sample of 15 and you found your sample regression equation, of which we reported the sample's slope. So we don't usually have the whole population, so we rely on our sample. But a regression line calculated from every value in the population, this population regression line, will have a similar format. So it's still going to look like a linear equation, but we're going to use some different symbols in it. So you're going to see here mu sub y equals alpha plus beta x. So the Greek symbols for it. Alpha in the place of A, beta in the place of B. So mu sub y, instead of just saying y hat equals, it's not saying that your predicted y value anymore.
The Oreos.
Thanks, Mr. Josh.
You're welcome.
It's not saying the predicted y value anymore. It's saying the mean y value for a given value of x. So that's what we're finding now, the mean y value for any x value you could choose. So alpha is in this position of the slope. So it is the population, I said slope, the population y-intercept, because it's in this position of the constant. And beta is in the spot of B. So it is your population slope. So again, when we have it from a sample, we're calling it a sample regression line, your estimated regression line. And we are familiar with y hat equals a plus bx. Y hat is the estimated mean y value for the given value of x. So we have the true mean value, the estimated, the population y-intercept, the sample y-intercept. We get all of these essentially point estimators. So that's the relationship we want to look at here. If we want to use the sample regression line to make an inference about the population, so this mu sub y equals alpha plus beta x, we can think of y hat as being an estimate for mu sub y. To find how the slope of the sample regression line b, so this is again sample, that's why you're seeing a b, this is what you would have calculated if we were in class. To see how it relates to the slope of the population regression beta, we need to learn about the sampling distribution of the sample slope. So this is an estimated sampling distribution of the sample slope because it's not every possible combination. But again, here's not every possible combination. So this is 3 possible different simple random samples of 15. So each graph displays the selected points and the least squared regression line for that sample. So the green is the sample. The population, which we know because again, we have all 263 population eruptions, is shown in blue. So there's a lot of similarity there, but the thing that we're focusing on are the slopes. We know the population slope is 13.29.
Okay, so run.
But if you compare that to the slopes of the sample, you get 10, 12 and a half, 15.7. There's a lot of variability in what these sample slopes are. And a variability happens, sampling variability happens, but we're trying to look at the pattern that happens each time. So instead of doing just a small sample, technology was used to simulate choosing 1,000 simple random samples of size 15. This is from the old faithful data. Each time the sample regression line was calculated and the figure displays the values of the slope B for the 1,000 sample regression line. So this would be, we calculated this group, we found B, you put it on the board, and we did that 1,000 times. The vertical line that's in blue is our point of reference. This is the 13.29. This is the population slopes value. This is beta. So what we can see in this, I guess a dot plot, but we can still see the basic descriptors for any type of graph. So we can see the shape. It is roughly symmetric, so we can see that this side is about the same as that side. Clearly not the same, but it's roughly symmetric. It is unimodal, so there's a single peak in the middle, so I'm going to note that. So I'm just going to note it's roughly symmetric. Unimodal. And yeah, and then the center, the place where this peaked is really close to that blue line value. And when this was calculated, these 1,000 SRSs, the average of those B's that were put in here actually has a mean of 13.34. That's the mean of these samples, B's. The true value is 13.29. They are really close. So I'm just going to put the centers quite close to the slope of the population regression line. So the center of 13.34 is quite close. And I'm going to abbreviate for boredom's sake. We get really, really similar values. Then we talk about the variability. The standard deviation of these B values is 1.40. So this is the typical distance they're spreading apart, deviating from this mean value. You're going to see that that's really close to the sampling distribution of B's of 1.42. So we'll talk about that in a second, but I'm not going to write that twice. That's what we have. So the figure below is a histogram of the B values. So instead of looking at a dot plot, grouping them slightly differently, And then right on top is a true normal distribution. Now this normal distribution has the population, the sampling distribution of sample slopes. I'm not used to saying that one. The average of that and the standard deviation of that. So that's how it was created. So this curve models the approximate sampling distribution of the slope really, really well. So if we take all possible SRSs, so not just 1,000, but all the ones that are possible of size 15, we get the true sampling distribution of B. So not the approximate, but the sampling distribution of B. The shape of it is approximately normal. The center, I intended to erase some of this, but clearly I didn't. So mu sub B is again meaning the mean of our sampling distribution of sample means. I keep saying means. Sampling distribution of sample slopes. It equals beta. So the center of it was at the population slopes value, which means B is our unbiased estimator of beta. If we had to guess one number, guess your sample slope. It's not going to be exact, but it's an unbiased estimator. It should be really close over time. The variability is some weird formula. We're not really going to get into where it comes from, but the standard deviation of the sampling distribution of sample slopes will be sigma over sigma sub x times the square root of n. So sigma is the standard deviation of the residuals for the regression line. For the population regression line, that's important. So we talked about that, well, was it unit 2 that we did this, unit 3, way back when. We talked about finding the standard deviation of these residuals. Your calculator spits it out, but this is for the population. If you have your population data, throw it in the numerator. Sigma sub x is a different standard deviation, which is nice and confusing. This is the standard deviation for all of our eruptions. So again, we have one that's a standard deviation for the residuals, and then we have a standard deviation for all your eruptions. So that's why one of them has the x, because those are the actual data x values. The other one is just sigma, which is the standard deviation for your population regression line. When you calculate that, you get 1.42, and that interpretation is always going to be similar to how we talk about the standard deviations. The slopes of the sample regression lines typically vary from the slope of the population regression line by 1.42. This is the typical distance from the, not center now, but I guess center, the slope of the population regression. So, some things to note about this. If I can get my bearings straight. So, the mean of the sampling distribution of B, so mu sub B, is always going to be beta. That's what we said earlier. So they're going to be centered at the same thing, at the same number. The standard deviation of the sampling distribution of B is approximately, so standard deviation of the sampling distribution of sample slopes, standard deviation of the residuals, standard deviation of all your population values, times the square root of the sample size that was selected. And the shape is going to be approximately normal. So those are the main facts that we will need when we talk about these distributions. And this formula has some things that we could talk about. I'm not going to talk about where it comes from, but the key things that we need to think of is how it influences the variability of your sampling distribution of sample slopes. So because your numerator, the standard deviation of the residuals, is in the numerator, when that number is larger, that's going to make the whole thing larger. If you start with a bigger number and divide by something, your result is going to be bigger than if you had started with a smaller number. So when sigma is larger, so is your standard deviation of the sampling distribution of sample slopes. Which means when your points are more spread apart from the population regression line, we should expect more variability in the slopes of your sample regression lines from repeated sampling or random assignment. Sigma sub x, the standard deviation of the explanatory variable, so of all, in the example earlier, the eruptions of Old Faithful, because it's in the denominator, if you make that number larger, you're dividing by a bigger number, you're making your result smaller. So when sigma sub x is larger, sigma sub b is smaller. We could think of that as if there's a lot of variability in the values of the explanatory variable. So there's a lot of variability in your x values. You're going to end up having a more precise estimate for the slope of the true regression line. It's kind of like not really increasing sample size, but you just are increasing the type of numbers that are in your sample, which leads to a more precise evaluation of the slope because you're not looking at such a small snapshot. You're looking at a big wide area. The value for n, square root n, is in our denominator. We've seen that before. With every other formula for the standard deviation of the statistic, the variability of your statistic is going to get smaller as your sample size gets larger, as your sample size increases. So we've talked about that a lot. A larger sample size is going to lead to a more precise estimate of the true slope. So we can fit a least squares regression line to any data relating to quantitative variables. Those aren't going to be useful if the scatter plot doesn't show a linear pattern. So it's only going to be a good line if you have a linear pattern. Inference about regression involves more detailed conditions than just, hey, is it a line? The figure below shows the regression model in the picture when the conditions are met, which we're going to get to. So what this basically means, if you have your scatter plot, it's kind of like tilted so we can see this 3D nature of this. You have your scatter plot, you can have possible different x values, and you are getting, in this case, it's the population. So we're getting mu sub y, but it's along this line. If you stop at any one of those x values, for each possible value of the explanatory variable x, the values of the response variable y will follow a normal distribution. So if you stop at any x, your y values will follow a normal distribution. So this, if you stop at this x instead, you're going to get a different normal distribution, but there's some similarities to it. For each possible value of the explanatory variable x, the mean value of the response variable mu sub y falls on the population regression line, the true one. So the center of these normal distributions will be on your population linear regression line. Because the regression line goes through the mean value of y for each value of x, we can interpret the slope as, what can we do it? As a change in the average value, because again, mu sub y is the average for every one increase in x. So every 1 unit increase. The variability, we're talking about how spread out these normal distributions are. For each possible value of x, so each stop you can make on this x-axis, the values of the response variable y will have the same standard deviation sigma. So you're not going to get a lot of, like, this one's really shallow and this one's super sharply peaked. You're not going to have that. They're going to all have a center on this line, and then their variability, how spread out they are, how wide these distributions are, they're going to be identical. So consider the population of Old Faithful eruptions for this geyser in this given year. For each eruption, x is the duration in minutes, and y is the interval of time in minutes until the next eruption. Suppose the conditions are met. We'll get to that in the next video because I'm going to pause it after this. The population regression line is found for us, and the variability around the line is given by sigma equals 6. So we're going to focus on the eruptions that lasted at x equals 2 minutes. So we're not interested in every possible thing. We are making a pit stop at one possible value for our explanatory variable. So at x equals 2 minutes. The average amount of time until the next eruption we can find because we have an equation for mu sub y. So we're going to take 34 plus 13 times the x value that we're stopping at. So 34 plus 26 gives us 60 minutes. Again, that's the average amount of time if we had an eruption that lasted 2 minutes. The amount of time until the next eruption will follow a normal distribution, and the mean will be on that line mu sub y, meaning the mean will be the 60 minutes that we just found. It'll be centered at that predicted average. The standard deviation will be 6 minutes because all of them have the same exact variability, so you can kind of see it below. We're having at this x value, it's centered at 60 because we found it with our population regression equation, and the variability for all of these normal distributions will be 6 minutes. Because it's normally distributed, you can use your empirical rule. So for about 95% of these eruptions, The amount of time, y, until the next eruption will be about 2 standard deviations away. So it'll be between the mean minus 2 standard deviations, which is 48 minutes, and the mean plus 2 standard deviations, which is 72 minutes. So if the previous eruption lasted 2 minutes, then you have an average amount of time until the next eruption of 60 minutes. But 95% of the time, the next eruption is going to occur